Hello and welcome. My name is Akan. In this tutorial, we are going to learn how to use the standalone program written in C++ in order to generate spin textures using the output data stemming from the simulation package VASP. The code itself can be found on GitHub, and this is a link to the page. As a starter, we will take a look at the manual. So in here is the documentation for generating, or in general, the usage of this code is given. Let me emphasize that there are two executables. One is meant to run in a Cyclone environment, and the other one in a Linux environment. We will take a look at the gnuplot scripts. These are important. Last but not least, we have a kpath date file, which is optional and not mandatory. What is required is that you have a GCC and G++ version greater or equal to this version for Cyclone. And of course, you should have installed the gnuplot version greater or equal to 5.0. All right, so let's proceed with the manual and click on the PDF file. This is the tutorial, so let's take a look at the contents. First of all, we will define the spin texture and talk in general about spin textures. Then we will continue with the application of this code. Therefore, we will prepare the K-mesh grid, and we will see how this code parses the output files obtained from the simulation package. In the end, we will draw the spin textures via the graphing utility gnuplot, so by employing the gnuplot scripts. So in here, we can see the spin textures, so 3 figures. But before talking about these spin textures, let me just tell you what a spin texture is or how it's defined. So basically, the spin texture stems from the coupling of spin and orbital motion of electrons. That is to say, spin-orbit coupling. A magnetic field is generated by the orbiting electrons due to their orbital and spin motion. Consequently, the interaction between these two magnetic fields gives rise to spin-orbit interaction. And this code is quite useful for the investigation of these non-trivial topological bands or systems. In this case, we have been investigating Chern insulators by analyzing the band structures obtained from the non-collinear calculations. On the left side, you can see the band structure. So the spin textures are plotted for this particular band here, marked by the arrow. So in this paper, which has been published in Scientific Reports Journal, we are discussing the perovskite-based superlattices showing a quantized Chern number of +1. The color scale indicates the projection on the z-axis, with red indicating parallel and blue indicating antiparallel orientation. The inclusion of spin-orbit coupling leads to a band inversion and avoided crossing of the majority and minority bands around K, which is displayed in the band structure here. And we observed or identified a band gap opening of, I do not remember, but it should be around 38 millielectron volts. Interestingly, the spin texture of this perovskite-based oxide honeycomb lattice is dominated by majority, the red components, in the larger part of the Brillouin zone, and exhibits, and this is quite crucial in orientation reversal of the minority spin components, which are denoted by the blue arrows here, happening or taking place close to K. This is consistent with the shock-induced band inversion between the occupied majority and unoccupied minority band around K. A closer examination of the top view plot reveals the in-plane variation of the spins. If you are interested in this system, you might want to take a look at the publication given in here. All right, but what you should bear in mind is that the spin texture is plotted for this particular band in here. Currently, there are two modules implemented. In here, we have a honeycomb lattice, so we have a K-mesh grid generator for the hexagonal cell, and we also have a tetragonal cell. So the results are also published in Physical Review B. You can find it here. So the spin texture, as I said, plots are not only restricted to systems with a hexagonal structure, which we have seen above, but also for systems with a tetragonal structure. So in here, once again, we have two arrows denoting the bands for which the spin texture is plotted. In here, we have I just put the side view plot of the spin texture. Great. Let's continue and take a look at the preparation of the K-point grid. The code itself employs the famous linspace method to create the K-mesh, including 900 evenly spaced number of points. And this is quite important because we will need these points sampling the whole reciprocal, sampling the Brillouin zone along the reciprocal axis kx, ky, and kz. In here, we will see how to execute the already compiled code, and then we will choose the desired K-point path according to your system. So if you have a hexagonal structure, we will use the first one. Otherwise, we could also take the second K path option. Then we will generate this K-points file for the VASP simulation and perform the calculation. In here, you can see the format of this K-points file. The first line is an arbitrary comment line. The second line describes the total number of K-points. Third line is standing for the reciprocal coordinates option, which is, so to say, abbreviated by rec. Fourth line, reciprocal coordinates of each K-point and its weight of 1.0, which can be seen in here. So if you're interested in such coding challenges, there is a Udemy course of mine dealing with scientific computing using the programming language C++. I will share the link to the Udemy course in the video description. Let's continue and proceed with step 2, so the VASP calculation. Here are some recommendations. We should use the charge car file for the non-self-consistent field calculation from the pre-converged non-collinear SCF calculation. Some flags which are important. And which is more important is that you have the files for plotting the spin texture. So we will, first of all, need the procar file, which includes the magnetization components, Sx, Sy, and Sz, for the atoms arranged in the order of the postcar file. We will need the eigenvalue file as well as the outcar for grabbing the Fermi energy of the system. All right. Step 3, running the main program. Before running the main executable, you should copy all the necessary files, proca, eigenval, and the generated kpath txt into the current folder where you execute it. Then we will run it, and here is a note which is quite important because the size of the proca file can be really huge, several gigabytes. After having performed the calculation with a finer grid, so we are referring to the 900k points, the main code can be executed. And here we have a snippet of the code itself. If there was no error encountered, then it will be continued with the next step of plotting the spin texture. So this would be the last step. So post-processing using the GNU plot scripts. We will take, in this tutorial, we will take a look at the side view plot. So we will employ the side view GNU plot script. All right. So let's take a look at how to use this code in action. For this purpose, I will open the folder in which I already copied the main executable file. I already prepared the files which are required for plotting the spin textures, which means that the calculations are performed in advance. Therefore, you will find the proca file as well as the eigenvalue file. In here, I noted the band number, so 2206 is the band number in which we are interested in. These are the atom numbers given in the postcard file, and I already took the Fermi energy from the outcar file. All right, so let's run this code. For running this code, you just type in point slash and main, so the file name of the executable. Hit enter. Did you already run this program in order to generate the kpath? If we type in yes, we will immediately exit the code. We could just do it. Do not run the code and waste your time. So let's rerun this code. This time we will go here with a no. Let's type in yes to continue. Choose the path you want to take. Since we are investigating a hexagonal structure here, we are going to type in F. These are the high symmetry points, so gamma, mk, gamma. Along these high symmetry points, the spin texture is plotted. If you are dealing with a tetragonal cell, of course, you would just choose the second option here. Let's say F, hit enter. Do you wish to run the entire code? Use same kpath as used for the DFT calculation. So the code is reminding you that you should just not switch in between, and you should take the same kpath which has been generated before. Let's skip this step at this moment and take a look which files have been generated now by this main executable file. The file which has been generated is a kpoints output file. And this one has to be formatted, which means that you need to follow the instructions given in the documentation. So we still need here the proper format for the VASP simulation. You would just type in here something like foo 900 and rec for reciprocal. I won't save this now, but keep that in mind. Let's switch to the code itself. So this one has to be copied to the kpoints file. Then you run the code or the simulation, not this code, the VASP simulation, and get back having the proca as well as the eigenval file. I already did this in advance, so you still need to do it. Then you come back to the step. Please type in yes to continue. So we will say yes. Now the information which are needed are given here. So we will need to enter 206 because this is the band number we would like to plot the spin texture for. Please type in the atom number. So currently only 2 atoms are possible. So we will say 25th and 26 atoms given in our postcard file and exit entering -1. Now it might take a while because the proca file in my case is quite huge. As you can see, it is almost 3.5 gigabytes big. So, but if there was no error encountered, you will see this message, rows and columns, and you should always follow the instructions given in the terminal here. Last step is that we enter the Fermi energy, which corresponds to 9.6024, and we still need the band number 206. Hit -1. Now we have all the files which we need in order to plot the spin textures. So as you can see, we have the most important file, and this is the data.dat file. This one, I already copied it, but you should do it. So copy data t file into the plotting directory. Let's change to the plotting directory. Let's type in ls. And now we should have the data file as well as the gnuplot script in here. For running the gnuplot script, you should bear in mind that you should have installed Xming server in advance in order to see the result interactively. So otherwise you would get a message like unable to open display when invoking the gnuplot script. So you need to modify the bash rc file accordingly. As I said, it's important that you also install the Xming server. For running the gnuplot script, you just type in gnuplot -p and sideview.gnu. In here, I created an animation where we will rotate the 3-dimensional graph, but this is just something I wanted to show because it's quite fancy in gnuplot. But you don't need it. So let's hit enter. And now you can see the result, which has been already published in the scientific report paper. So this, by using this code, it allows you to gain an insight into the details of the band inversion mechanism. All right, let's take a look at the PostScript file, which has been generated now. Let's open this PostScript file. And as you can see, this is the last step where the animation ended, which we created using the gnuplot script. Of course, you don't need it, but this was just quite fancy to show. In this sense, I hope that the tutorial was helpful for you, and if you have any questions, do not hesitate to contact me.